Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Alhamdulillah wassalatu wassalamu ala Rasulillah. So I will continue with the lecture 3 on the combined stresses, and in this lecture we will look at examples where we will combine all the loadings due to um, axial force, bending moments, and also torsion. So that will be the final part of the combined stresses. So we have covered these three simple stresses, which is normal stresses due to axial loading, and then we have got shear stress due to torsion, and this is finally we've got stresses due to bending moments. So we normally look at the shaft, and then you have got this axial loading, your number one, and then you've got shear stress due to torsion, T, and then finally you've got this bending moment, M. And each of them will create stresses on the parts, as you can as well remember that when we apply a axial force and we look at the differential element, the stress will look like that. If we have a torque, when we apply a torque, T, the stress would look like this. Yeah, going down. Okay. And if it is a bending moment, it is sensitive to your neutral axis. So this is your M. Yeah. So, and then depends on where you are. On the top, you will have compression, and at the bottom here, you will have tension, depending on the bending moment. So these are the three skills or what we have done under the past two lectures. So and this is what we were doing. We were drawing the differential element. So looking at the differential elements, these are the differential elements. So by now, some of you might have achieved the ability to draw the stress differential element and able to label all the force, all the stresses acting on the elements. Okay, so we'll do it another example. So the key learning point is for you to be able to sketch the stress acting on the differential element and your ability to visualize the stress. Okay, so and then you have to in order to do that, you have to calculate the stress created by each force, and then you put the stress values on the differential element. I'll repeat it here. For example, this is your axial load, and you want to find the stress acting on the differential element, so you know what that is, and then on that stress you now know that it is in tensile. So this is what you do. Similarly to torsion, if you have a torsion T, you look at the element here, just follow the direction of the torque, tail to tail, head to head, sorry, yeah, this, so that's your differential element. And your for bending moment, you must know where your neutral axis is, and then here the bending moment, on the top there is compression, and at the bottom it is tension. Yeah, so that again I'm trying to make sure that you can all draw the differential element and label the stresses acting on the differential element. So let's do one example here. A shaft of diameter 20 mm is subjected to axial force F equals to 40 pi n and bending moment M equals to 4 pi Newton meter and a torque of T equals to 10 pi Newton meter. Draw the stress differential element of point P. Point P is here, and then point Q. Point Q is located at the neutral axis of the shaft. So what do we do? Okay, so point Q is located at the neutral axis. This is located neutral axis, and A. So let me write it, neutral axis. So, and then draw the number one is calculate the stress due to each force at P and Q, and draw the differential element of P and Q. So I've calculated here the value of I, i.e. the second moment of area of the shaft, and the I has been calculated here to be 2.5. That's your value of I. Okay, and then I've calculated the area to be 100 pi mm square. So 2500 pi di. Why do I need this? Because later on we will use this to calculate the bending moment. So from the axial force, we know we are looking at this axial force. I'm looking at this axial force. Yeah. So I have to calculate. I have to determine the stress at axial force due to axial force at point P and A. So again, we know the stress is equals to F over A, and we know what F is. F is 40 pi Newton, and then A is 100 pi mm square. Yeah, so you got 0.4 megapascal. So it's uniform. We know that axial force is uniform. So at P, the stress element is all tensile. So I can do it like that, 0.4 megapascal. And for Q, it's also uniform as P, sama saja. So it's 0.4 megapascal. So that's done for axial force for point P and Q. And let's move on to the next one, which is the bending moment. So bending moment due to M, I'm looking at bending moment here. Okay, so I'm not looking at tau or F, just individual bending moment. So the general formula for bending stress is my over I, and in this case M is given 4 pi, and then I is also given 2.5 times 10 to the power of 3 pi. This is mm to the power of 4, and then kita ada value of y. Yeah, so what we have is 4 divided by 2.5 y times 10 to the minus 3 megapascal. Yeah, so our M is for P, y equals to 10. Yeah, so sigma equals to 4 divided by 2.5 10 times 10 to the minus 3, so equals to 4 divided by, yeah, I'm going to leave that, 2.5 times 10 to the minus 2 megapascal. Okay, and sorry, M is 4 pi Newton meter, so I have to use a Newton millimeter, so I need to type this as times to the power of 3. Okay, that, let me redo that again. Made some mistakes here. So for P, sigma equals to 4 pi times 10 to the power of 3. This is Newton millimeter. And y is 10 mm. 10 mm. And then I is 2.5 pi. 2.5 pi times 10 to the power of 3 mm to the power of 4. So now we can somewhat do the simple question is equals to 40 over 2.5. So megapascal sama dengan 10 4 16 to the 16 megapascal. So we can draw, it is at P it is compression. Yeah, so this is for V. And for Q, similarly y equals to 10. You can repeat the calculation, but you will have, it is now it is also 16, sorry, it is 16 megapascal, but I've made a lot of mistakes here. Here y equals to 0. Okay, so sigma equals to m y over I, because y is 0, and it becomes 0. So I can draw the differential element just like that. There's nothing there. So this is for Q. We've done that. This is for Q, and this is for P. Okay, so we have the answer for bending moment. And then we have for torque. For torque, we have tau equals to d r over j. So at P and Q, the same thing. R is equals to 10 mm. Okay, and the torque is the same. Torque equals to 10 pi. And J is pi d over 4 over 32. That's equals to pi 20 times 4 over 32. So we can calculate tau equals to 10 pi times R 10. All units are in millimeter. 10 pi Newton millimeter, so we have to times 10 to the power of 3 times 10 to the power of 3. I'm going to put the unit here just so that it reminds me my units, times 10 mm, and divided by pi d over 32. Yeah, so we can start to cancel things out. Yeah, so it's 10 is equals to 32 times 10 to the power of 5 divided by 20 to the power of 4. Yeah, so that will get us to lebih kurang 32 bagi 16, 10 to the power of 5, and then 2 kali 10, 10 to the power of 4. Yeah, so that will give us 2, 4, 16, that is 20 megapascal. So if I were to draw, I will take the direction. I look here. Oops, sorry. So I were to draw that. We've got the um, just now. It's like this. So P is up there and Q is here. Again, we'll just follow the stress element. Okay, and it is 220 megapascal. Just now we have calculated that to be 20 megapascal. For point P and point Q, if we draw it like this, it is like that. Okay, so it's 20 here, 20 there, maybe the units. Okay, so there you go. We have now calculate or draw the stress differential element for all. This is for torque. This is for torque. Okay, and then at P also we have got these stresses due to axial load, and then finally due to bending moment. Okay, at top is a compression, and at bottom it is tension. Yeah, so let me take this out. So you can add all these things to be the final shape of the stress element. So there was, this one is 20, and this one is, can you just add that, bending plus axial, and this is 20. For the bending moment just now, our this is 0. Yeah, so we only have, therefore our stress is only due to axial, and this is 20. Okay, all right, so I hope this is clear to you how you finally get the differential element due to the stress from each loading applied to the structure. Okay, so let's look at the next one. So this is an example where so let's look at this example where we have a shaft, and where we have a shaft, the diameter is 20 mm as before. Okay, so I need to draw the diameter. So diameter is 20 mm, and then we have two loads. One is 100 pi Newton in the axial direction, and the other one is 200 pi Newton acting on a crank at a distance 150 mm from the centroid of the shaft. Okay, and we are asked to determine or draw the stress element at point P, Q, and R, where the cross section is 120 meter, 20 mm from the free end of the shaft, and P and R is located at the top and bottom of the shaft, and Q is located at the neutral axis. So maybe I have to, yeah, there's already showing you the location of this P, Q, and R, and this is the neutral axis. Right? And I took the opportunity to label the axis here X, Y, and Z. Okay, so as before, we need to do the some basic calculation of the I and A of the shaft. So the first step that we need to do is to step one is to transfer all the load to the centroid of the cross-section area. So where is the centroid? The centroid is here. I'm going to use this yellow pen to highlight the location of the centroid. So we need to transfer all the load to the centroid of the cross-section area. It means what? It means that I need to transfer this 200 pi Newton to here, and I need to move this to here. Okay, so let's do one by one. Let's say if I were to move the load, I were to move this axial force to here, that is not a big problem. I am not moving away from the line. They are sharing the same line of the centroid, so I can safely move it there. There is no moment created. There is no moment created. So maybe I'll just to extend the line here. So I'm going to extend the line to here. So the next thing is for me to move this 200 pi Newton. 200 pi Newton from this location, I have to move it to here, and I have to move it here. Okay, if I were to move 200 pi Newton to the in the z-axis, so I will create what we call a torque. So that is, if I move from point, let's say, let's label this point. If I were to move from point A to B to C, yeah, so I'm moving from A to B now, like I said, moving A to B. So this 200 pi Newton will create a torque of 150 mm, yeah, times R. So that gives me 30 times 10 to the power of 3 pi. This is Newton, Newton mm. So it's Newton mm. So this is basically a torque. Even though I can put it as moment about the x-axis, it is equals to the torque T. So it's 30 times 10 to the power 3 of pi Newton millimeter. Now I move from point B to C. From B to C, I am moving it in the, let's say, along the z-axis. So from B to C, I have to move this along the x-axis. Along the x-axis. So guys, I am moving it from B to C. B to C is 120 mm along the x-axis, and that created a moment about the z-axis. So this created a moment about the z-axis. So moment, I'm just writing that mzz, z-axis, which is equals to bending moment. Okay, and that is equals to 200 pi times 10 to the power of 3. Sorry, this is not 10 to the power of 3. 200 pi Newton times 120 mm. Okay, so this is our bending moment. M equals to 24 times 10 to the power of 3 pi Newton millimeter. Okay, so now I have successfully transfer all the forces here, bending moment and torque. So this is now, this force is now here. So I can draw it. Can I draw it? Can I erase this? Is it possible to? No, I cannot erase this. So I have to show it in here. Maybe I can. Oops. So that's the loads transferred to the centroid. Yeah. So 24 times 10 to the power of 3, 100 pi, and then I got the load 3 T equals to 30 pi times 10 to the power of 3 Newton meter, and also a vertical force of 200 pi Newton. Yeah. So that's basically the force that is uh, doing for the calculation. So we have the torque, the moment. We've got the torque. This is the torque. We have got the torque, the axial force, 100 pi, got the bending moment, and also remember we were transferring this vertical load from here to here. It now is there, 200 pi Newton. Okay, so what we have not covered so far is what is the effect of this shear force on the distribution of the shear stress along the surface. Okay, so this is going to be a bit tricky, but let's do them one by one. So we have 4 loads here acting on the system. Okay, this is load number 1, this is load number 2, this is load number 3, and this is load number 4. Okay, so load number 1, let's do one by one. Load number 1 equals to stress equals to F divided by A, and that is 100 pi Newton divided by pi. R square, R is 10, so 10 square. So we have got 1 megapascal tension. Okay, so and then we have load number 2. Load number 2, this is uniformly distributed. I'm not going to do individual yet. I'll just solve one by one. So tau equals to TR over J. Okay, and the torque is given there, 30 pi times 10 to the, this is Newton millimeter ni, times 10 to the power 3 Newton millimeter, and then R is 10, and then J is pi over D to the power of 4, 32. Okay, so we can cancel that out. So it becomes like 15 to 0, 2, 16 kali 32, 16 times 32, 16 times 32, to 2002, then 32. So it's 522. So it's 522 megapascal, if I'm not mistaken. I might be wrong here, guys, so you have to check with your calculator. Okay. So again ya, 30, 640, 6, 326, no, so 96 divided by 2 is 46. No. 92 divided by 16. Yeah, 92 divided by 16 is 92, 92, 16, 16 by 5. Yeah. So 522 megapascal or 52.2. 32, 16, 10, 4, habis. So 64, 30 bagi 64, 30, 30 is 0.522. No. 96 bagi 2. Am I right? No. Okay. Yeah, this is kali 2, 96 divided by 960 divided 916. Okay, so the third one is, oh no, what happened? So So we have calculated here the stress due to the axial force, sigma A equals to F divided by A, 100 pi by pi 10 squared, so it's equals to 1 megapascal. So at P is also tension, this is tension, yeah, as we have done this before, yeah. And then Q we label as tension and R we label as tension, and this is my reference axis. So let's move on to the next one. So the load due to the bending moment, I have to put here 200 pi. I always forgot this 200 pi is acting here. 200 pi. So bending moment is my over I, and it's now let's say this is 32. I'm changing that to 32. So M is 24 pi. Oh no, I cannot change it. So sorry. This one maintained as 30 because it comes from the 20. So 24 pi times 10 to the power of 3. Then I kita dah kira tadi. Pi 20 to the power of 4 over 64. And then times y. Y is 10 mm. So this is Newton mm. And this is mm4. So I'll just put the unit there for us to be very clear. So so this becomes like, we can remove this. Yeah. So hold on, let me do that. So the bending stress is 9.6 megapascal at the value of y equals to 10. So at P, y equals to 10, and therefore the bending stress is 9.6 megapascal. And because of the direction of the bending moment, it is P will undergo tension. Yeah. So because it's the beam will look like this. Yeah. So yang ke atas tu akan mengalami tension, and then at the bottom tu akan undergo compression. So similarly at R, y equals to 10, but now the bending stress is 9.6 compression. And then at Q, y is equals to 0. So bending stress is equals to 0. Yeah. So you can now draw the stress elements at P. So if it is at P, it is 9.6 in tension. Oh, sorry, yeah. And then this is at P, and this is at Q, is 9.6 in compression. This is at Q, and then at sorry, this is at R, and at Q there's nothing, it's 0. Okay, so and just remember your coordinate system. This is going to be X, Y, and Z. Yeah, so that's the stress due to the bending moment. And then we have got the stress due to torsion. So when you've got the stress due to torsion, is T equals to tau, tau is equals to TR over J, and the torque is given by 30 pi times 10 to the power 3, not Newton meter, Newton millimeter, and then R is 10 mm, and J is pi D 4 to the power 32. Yeah, so you can calculate tau to be, so tau is equals to 6 megapascal, and you can draw the element there. Just follow the direction of the shear or the torque applied. So at P, so I'm going to draw my X, Y, Z here. X, Y, and this is my Z. Yeah. So at P, tau, at P I have to draw terus lah, is 6 megapascal. Okay. 6 megapascal. At Q, also 6 megapascal. And then at R, I'm looking from the bottom here. Megapascal. Yeah, so my eyes at R, my eyes is here. My eyes is from the top, so I'm labeling that. So this would be my Z, and that will be my X. If you want to see where it goes at R. So this is the stress due to torsion. So we've got, so one is, what is missing is the other one, which is the 200 pi force there. So when you apply the force, 200 pi Newton is acting parallel to the cross-sectional area. So that force will create a shear stress. Okay. And this shear stress is distributed. It is not a typical shear stress, so it's a shear stress distributed in a beam. So it's distributed in the shaft. So what is the distribution? How is it distributed? How is it distributed? Okay. So if you do not know, you could make an assumption that tau equals to F divided by A. Yeah. And then you can say 200 pi divided by A pi r square, 10 square. Yeah, so it's 2 megapascal. And you say that, Prof, why don't we just distribute tau along that surface here? That's one way of assuming it is distributed. But in actual fact, this is distributed according to the value VQ over IT, where V is the shear force, in this case 200 pi, Q is the first moment of area, I is pi d 464, and T is the thickness at the section. Okay, so first moment of area. So it is distributed in the form like this. So if you look from the side, this is Q, this is P, and this is R. It is distributed in this form. Okay, so that's how tau is distributed. So tau is, so from this distribution you can find that tau is 0 at top and bottom of the beam. So at P and R, tau is 0. And tau equals to tau max at Q. Yeah. So, and how does it look like? It looks like, how do you draw the shear stress distribution at P, Q, and R? Is gonna be quite tricky because it is now acting at element that is not, the stress is shear stress. Let's draw the plane here. So it is X, Y, Z. Shear stress is in the YX plane. Okay, and because of the scope of this study, we are only interested to plane stress. And therefore, we will sort of ignore. We assume that the shear stress due to vertical force is negligible. So this is the limit of the techniques that we are using now. We can look at the plane stress, and we have done the stress differential element, and after that you just combine all the stresses, yeah. So so what I want you to do is just to combine for P, for example, take the stress axial plus the bending stress okay, plus the shear stress due to torque to create your differential element. And you can repeat the same thing for Q and R. Special thing about Q is that you only have axial stress, yeah, but you don't have 0 here, and you have a shear stress. Okay. And R, at R because it's at the bottom. It is again sigma A is the same, but the bending stress is compression and shear stress is the same. Okay, so you can draw all the elements, differential stress differential elements. So by that, I hope you have at least understand how to draw the differential element. Go parts by parts, load by loads, and from there you can draw the differential element. You can also look at other lecture materials on the YouTube to assist further understanding. Yeah.